Okay, so coming back into this last example, once again, we had let u be x cubed. We had noticed that that was going to be a nice tan inverse when I took the integral. So I went ahead and did my u substitution. I took the derivative. I isolated my x squared dx, which was perfect. When I separated my integral into the u part and the x part, we noticed that was a perfect substitution. So I'm plugging this in for the x squared dx. I get 1/3. I get 1 over 2 squared plus u squared. All of this, remember, was replaced, so that became a du. Perfect. Now I'm ready to do my antiderivative. I've got the 1/3 out front. I've got 1 over a. Remember, a is your constant out here, so that's just a 2 times the tan inverse of my function, which is u in this case, or x cubed, over a, which again was 2, plus c. So finishing this up, I've got 1/6 tan inverse of x cubed over 2 plus c. All right, so in our next example, now once again, we have a couple of options for how we can solve this question. So one of the things I still do is I always try u substitution. So like in this case, I could let the whole bottom be u. If so, I get du equals 2x, excuse me, du over dx, which means that du equals 2x dx. And then I could come over here and see if that works. Maybe it will, maybe it won't. So this becomes x over u dx. If I separate my u and my non-u stuff, hey, that actually works out nice. So I don't need to use a trig relationship. So you guys got to watch out for that. So this becomes a 1/2 1 over u, all of that now is my du, and then I can just nicely make that the ln of u plus c. So this becomes 1/2 ln of x squared. Oops, let's get that absolute value in there. In both places, my bad. X squared plus 25 plus c. So you have to really be paying attention to it, because what I didn't need to do here was use that tan inverse relationship. So if you're asking yourself, well, why couldn't I have used the tan inverse relationship? Well, let's take a look at that. In fact, I think that's good enough to put in a new page here. So let's do this question as if we were going to use that. Because again, as you do some of these, you're going to start to think you can apply it one way, and maybe you can and maybe you can't. So let's see. So let's say you thought you were going to use this as a tan inverse. And so you said, okay, well, here's what I noticed. I noticed that I have something squared plus something squared, right? Okay, and so if that's the case, remember your u would be x then, which means your derivative would be 1, which means, and here's the reason I know I wasn't going to use this version. That means that when you went to solve this, you would have split it up into your u stuff and your x stuff. I hope that you see the problem with this. There was no x to replace, so I could not have used this version to solve it because this wouldn't have been a direct relationship. I would still have x's basically in the problem. So again, the only way to solve this one was to actually go back to typical u substitution. So you have to ask yourself which one's the better way to do as you're doing these problems, because I will flip back and forth in how I want you to solve them. Okay, so in number 9, which is our last problem for today, it looks like nothing that you've seen before. So don't let it intimidate you. So on this one, obviously, if I was looking at my possible inverse trig functions, it doesn't seem to fit that because I don't have something squared plus something squared. I also don't have a square root on the bottom, so it's definitely not going to be a sine inverse relationship. So how do I solve something? Well, you could try u substitution, letting the whole bottom be u. We could absolutely do that. When we do the integral, we end up with 2x plus 6, which even if I did factor out a 2, guys, ends up with something like this. And unfortunately, if you'll notice, if your whole bottom is u, there's no x's left to replace. So that's not going to work out. So letting the bottom be u isn't going to work here. So we need to find another way to attack this. So this is going to take some stuff you learned in actually Algebra 1 and probably practiced in both Algebra 2 and Pre-Cal, and that's something called completing the square. What we want to do is produce a relationship like this, meaning I need it to be something squared plus something squared on the bottom so that I can use this tangent inverse relationship. Okay, so how do I do that again? To complete the square, and I'm actually going to do it off to the side. To complete the square for something like x squared plus 6x plus 13, okay, I want to find this value. I want to find something where it would create a relationship where the perfect binomial squared produced this. So most of you probably know if I were to square a binomial and I want my middle term to be a 6, this would need to be a plus 3. So that when you expand it out, you get 3 times x times 2 or 6x. And if this was a 3, then that would make this position have to be a 9. Okay, so then if I look at what happens after I plug that 9 in, this new relationship does become a completed binomial, but you snuck a 9 in. So because I snuck the 9 in to create this, I would have to take that 9 back out over here. Otherwise, I don't have the same equation I used to have. So if you sneak a 9 in to complete the square, you have to take the 9 back out. So then that actually becomes a plus 4. So this bottom is the same as 1 over x plus 3 squared minus, or excuse me, plus 4. Now, if you don't believe me, square it back out, add it all together, and you still get this. So how is that helpful? Well, then that produces something where I have something squared with an x involved plus something squared that's constant. So it's kind of backwards because I have my constant listed second and my function listed first, but that's fine. Okay, so I still have to do a u substitution, so I'm going to do that off to the side here. So I've got, let me get rid of some of these stray marks. So I've got my u will be x plus 3. My du over dx is just a 1, which is wonderful. So that means I have a relationship for du that's a straight relationship for dx. So that's going to make it very easy to plug in. So let's rewrite with u's. So I've got 1 over u squared plus 2 squared dx. Again, this is the only part I need to replace, which is perfect because that's a du. Everybody's in terms of u. And I'm ready to do the integral. So the integral is just 1 over a. Remember, a is the square root of your constant, so in this case 2. So 1/2 tan inverse of u, which is my function, which in this case, again, is x plus 3, over 2 plus c. Okay, so as you can see, guys, some of these get very tricky. I think when you're doing these relationships, my tip-off would be this one you need subtraction and you need a square root. This one is addition and obviously there is no square root. You got a lot here to practice. As you can see from my previous example, let me go back real quick. Like in example 8, remember sometimes you can use those relationships we learned today and sometimes you can't. Sometimes doing that isn't helpful. And so sometimes you go back to just letting your whole denominator be you. So it's trial and error until you get more confident at seeing it. And there will definitely be a time when you get to a place where you say, oh no, the U substitution is not going to work. I can tell it. You could do it in your head and you can see that it's not going to come out helpful. So you'll just learn these techniques and get more comfortable with them as we go on. So enjoy your problem sets and I'll see you in class.